Right, welcome back everybody to a new lecture by the Machine Learning and AI Academy, where we're going to be describing variational inference. This is one of a series of lectures where we will be describing different forms of variational inference. In here, we will just be talking about an introduction, the evidence lower bound, and a relatively simple algorithm to optimize for that. We would like also to thank everybody who participated in our survey. So we had 91 people answering, and the most votes went to variational inference. That's why we're giving this lecture about variational inference. That being said, other people were interested in other notions of machine learning that we put there, and that's why we're going to be discussing these as we finish and go in turn. So we're going to begin by a motivation and describe Bayesian modeling, to which variational inference is a tool in order to solve. And we're going to say why Bayesian modeling is really important and why is it interesting to think about. So maybe it's not mainstream in machine learning. However, probabilistic modeling based on Bayesian modeling really is very widely used in machine learning. And it is one of these approaches that is maybe more principled to do than neural networks when it comes to machine learning. So the way probabilistic modeling think about machine learning is that we should model probabilistically a certain event that is happening, or like certain data types are probabilistically generated. And neural networks are just tools that we can use there in order to have a representation. So such an idea has been, for instance, used in image generation, where we have a training data and we try to learn a distribution from which we can sample data that is close to the training data. It has also been used in trying to predict protein contexts, and that's kind of like trying to understand how proteins interact with each other. And also, it's been used by big companies, maybe Uber and others, in order to do taxi and fare analysis. So here are just two examples from Trippi et al. 2018 and Kuckel-Kilber 2016. And the idea of Trippi et al., for example, is that they are trying to predict the distribution of the fare versus the tip in certain areas in New York City. So on the x-axis here, you see the fare. On the y-axis here, you see the tip. And in the fare, for example, you can want to predict, okay, what is the distribution of having a $5 fare in that location that gives me a tip of 20%. So here you see these colors. The darker the color, the more density we have that this thing can occur. And it's interesting that these are full distributions generated by the model. So it's not just a prediction about, okay, what is the mean that this event can happen, but it also tries to give me the whole distribution by which this event can occur. So it also has been used in modeling epidemics. So for example, Lloyd et al. Tried to use it in order to model epidemics in Nairobi, as well as in other places. And then it is also very, very useful for stock markets and time series analysis. So for example, if you want to do any trading, it's preferable that you have a probabilistic model capable of giving you the whole distribution of your predictor. And also has some very cool applications in sports. So for example, Deng in 2017 used it in order to model Steph Curry's intensity and posterior uncertainty in shooting 3 points. And again, this gives you a whole distribution, and it displays where Steph Curry is more likely to score, where Steph Curry is more likely to fail in scoring. Now, what is so cool about probabilistic modeling? Like, why do we need probabilistic modeling? Now, this is something I believe is very, very important when it comes to machine learning, and that is that probabilistic modeling allows us to quantify uncertainty. Now, this is really important. So nowadays, if you think about a neural network, you cannot really get an uncertainty estimator from that convolutional network. Let's say if you're trying to estimate or predict images. When it comes to probabilistic modeling, this is interesting because it can give you an output of the whole distribution, telling you how sure the model is about the prediction it made. And when it comes to safety critical applications, say self-driving cars, or even when you're trying to buy or sell in a stock market, it is really important to understand how sure your model is about the prediction. If my model says that the price is going to go up and it's 10% sure, maybe I don't want to buy that stock. So the idea of uncertainty quantification is really, really important when it comes to machine learning, and that's what probabilistic modeling allows us. So here's an example from some of the old colleagues I had back at Prowler.io, and these guys have published a paper recently trying to quantify the uncertainty of making mistakes in image prediction by using a convolutional neural network, a convolutional Gaussian process, which is a Bayesian modeling approach. It's a non-parametric method, and a translation invariant Gaussian process, I guess. That's called TIC GPs, and that's, I think, the approach proposed in that paper. Now, it's really interesting. So what they are plotting here is they are trying to tell me the belief over what the output of the model is. So, for example, in a convolutional neural network, this figure here is believed to be number 4, and maybe kind of 1 is not apparent on this scale. So the network is kind of sure, oh, this is a number 4. However, if you and I look at this figure, we're not sure it's a number 4, we're not sure it's a 7, we're not sure it's a 1 really. It might be between either a 1 or a 7. So the TIC GP says, well, okay, I believe this is a 7, but also I believe it's a 1. And that's really interesting because now the model is capable of telling you how uncertain it is about certain predictions. And this is something you can also see in, predicting some other numbers here, which are not clearly cut between like a 4 and a 5 or a 4 and a 7 and so forth. So that's in like static cases, which is also which is very interesting and important. However, having Bayesian models that can quantify uncertainty is also important in dynamic problems such as reinforcement learning. So here are two works from Dijsselroth et al. In 2011, and that's PILCO, which is kind of like the maybe arguably state-of-the-art model-based framework. At least in low dimensions, nothing can beat PILCO so far, and it has been published in 2018. So the idea of PILCO is that it tries to have a model-based RL solver where it tries to learn the model, but it also tries to quantify the uncertainty by learning the model using a Gaussian process. Based on that Gaussian process, then it tries to explore. It updates the policy, and then it tries to explore in the environment based on kind of the uncertainties from that GP. So there are two versions of it. One version does that. And as you can see, it reduces the number of interactions needed by the system in order to learn something very useful by orders of magnitudes. This is also another result from one of my recent papers about multi-view reinforcement learning, and we can also see that if we use such a principled approach, then we can also reduce the number of interactions in order, I think this was to park a car or something, in order to do that. So now, in essence, this uncertainty quantification is important, as we said, in safety critical applications or in the reinforcement learning applications, but also you gotta be very careful when you, for example, try to do trading. There are a lot of blogs out there trying to do trading based on recurrent neural networks and stuff. Well, all that is great, but at the same time, I would be very careful putting my money based on a prediction from a recurrent neural network, because these rarely have uncertainty estimation accompanying them. And we really need these uncertainty quantifiers in order to understand what is going to happen. I am very sure about my prediction or not. So that's really, really important, and that's what probabilistic modeling allows us. Now, there is another point to be made here, is that there is some interest now from the neural network community trying to do uncertainty modeling, and that's all great. However, we're not going to dig into that in this lecture, but one has to keep in mind the difference between calibrated and uncalibrated uncertainties, and the methods that are out so far, they are not clear cut on that. So it's worth thinking about that a little bit. However, these models, they provide some uncertainty estimators to an extent that we know is more or less correct. And that's why when it comes to, for example, reinforcement learning, they can be useful. When it comes to trading, they can be useful. That's why most models that are used in the financial data analysis nowadays are actually based on these and not based on standard neural networks. Right. So in order to think about probabilistic modeling, we have to change a bit our way of approaching machine learning problems. So nowadays, if you are thinking about a machine learning problem, you would think about a neural network, input outputs, maybe having some form of an error function that you would like to optimize. Okay, all good. However, what we're going to do in this lecture is change our perspective a little bit and try to think about machine learning from a probabilistic perspective. So we're going to say that we have some observed variables. So take like the set of images you have, or the set of points, or some trajectories I've seen from the real system or something. And now what I'm trying to do is I'm trying to infer some latent relationship which generated this data. So the idea is that I give you a set of data and now you step back and say, all right, I believe this data came from some model of nature that is hidden to me. And what I'm going to try to do is I'm going to try to learn that model in order to get as close to the nature's way of producing this data, of course, under my assumptions. So nature has some process by which it generated data. I'm going to try to model that. In order to do that, I'm going to put some assumptions and I'm going to try to infer that way of nature generation of the data in under my assumptions that I put. So we represent this process by a graphical model that looks like this. Again, we have an observed variable x and we have a latent or a hidden variable z. So again, as I said, there's some hidden process, and in order to represent that hidden process, we're going to introduce a latent or a hidden variable. And now this arrow here is a conditional dependence relationship, which really means that the distribution of x is actually conditioned on this z. So x is a random variable and z is another random variable. And now we have x conditioned on z. That's how we observe our data. So this here is kind of like what nature is doing in the background. And I'm trying to model that process that nature is doing. Now, in order to be general, we keep this x as a vector from 1 to n. So for example, let's say you have, 10 images, each of some d dimension, flatten them out, let's say, and then you would have a long vector of size n, and that is this. Or you can say, okay, each x itself is an RD vector, and I have n of them. That's equally possible. And we're going to have m-dimensional z variable or m-dimensional latent vector. So a latent variable model, it will allow us to infer about the hidden information not observed in the data. So as we said, the process that's hidden, we're going to try to learn that. And it's a principled way to introduce our beliefs and the priors. Remember, I told you we're going to put some assumptions in there. We're going to say nature operates in this way. So in order to do that, what we're going to do, that allows us to put all the priors. I believe nature's latent distribution is coming from a Gaussian. So these are things I'm putting in, and it's a principled way that allows me to put my beliefs and priors on the phenomena that I'm trying to model. Now, as in any other machine learning method, in order to train this model, we would need some form of an optimization problem, right? So we would need to have some optimization problem that we want to maximize or minimize something in order to infer all the free things in this model. So that in a probabilistic model is that we want to maximize the log of the marginal, so p of x. Remember, these are our observed variables. So the data we see is actually in x, and that's the only thing we see, right? So the idea here is that we're going to try to maximize the log of p of x, the log of the marginal distribution of x. If we are able to maximize that, then we're going to have a model that will have a high chance in producing the data we have seen. But now, as we said, we are introducing some hidden or latent variables that describe the process by which nature is producing for me these points, and we need some principled way to introduce it into this equation. That principled way is simply through marginalization. So you know from your probability courses that if you integrate out a variable, you would get the other variable. So for example, if you have a joint distribution over x and z, and then you try to integrate out with respect to z, then you simply get p of x, right? So the whole idea is what we're going to do to go from here to here is we're going to assume that this arrived from a marginalized out distribution with respect to z. And now that's interesting because you remember philosophically we were just discussing that there's some hidden process of nature that's generating the data and we're trying to model that. Well, that's exactly what we're trying to do here, right? So we have this hidden thing and we're trying to marginalizing it out, saying that, okay, what we observed was something done by nature, but I don't observe its hidden structure and I'm going to try to learn that. So in order to go from here to here, we simply just marginalize out z. And now, This is a joint density, and we can factorize a joint density using Bayes rule. And the Bayes rule says, if you remember, P of A and B is P of A given B times P of B. So P of X and Z is P of X given Z multiplied by P of Z. And of course, there's the integral, which is marginalizing everything out in order to get back to P of Z. So now, as you see here, we're going from the marginal into this marginal, and now our goal is to maximize with respect to some parameters which you don't mention here, we're going to come to them in a second, this equation. Now, all good, but at this stage you should be worried because computing this integral is actually a nightmare. It's not easy to compute this integral dependent on the assumptions you have made about P of X given Z and P of Z. So for example, if you said that the distribution of X given Z times P of Z are both Gaussian, then this integral is kind of easy to compute. If you had the conjugacy between P of X given Z and P of Z, this integral is easy to compute. But sometimes you don't have that, and in most interesting models, you don't actually have that. So how we compute this is the whole bottleneck of Bayesian inference, really. And now there are multiple ways to compute this. So there are sampling methods like Monte Carlo techniques, for example, and Markov chain Monte Carlo techniques. And there are variational inference methods that allow me to approximate this integral. But let us understand this more. So before diving into that, let us take an example. So the example we're going to take is a clustering example, which should be familiar to most of you. So in clustering, you're given a data like this, right? So you have all these data points here, and you're given these data points, and you want to, cluster them together based on their distance relationship. So for example, here you would say, okay, I have 3 clusters, and this is one, this is another one, this is another one. So the way you would approach that maybe when doing standard machine learning is by just doing k-means clustering, right? And then you kind of minimize the distance between the points, and then you figure out the best clusters. Okay, good. But what we're going to do now is we're going to think about the clustering problem from a probabilistic modeling perspective. We're going to say, okay, we have n data points, and we know that there exists k clusters. So in this case, 3, k equals 3, for example. We know that. To infer the cluster number, we can still do that, but that's kind of a more advanced lecture. We can do that later. For now, let's assume we know that we have 3 numbers of clusters here, or k number of clusters. So now your goal is to infer kind of the nature's process by which it generated for you these clusters. So the idea is that you observe this data and you start thinking and you say, okay, nature, how would nature have given me this data? And then maybe one way to think about this is that, okay, maybe nature has access to k clusters. It picks one of these clusters. Out of these clusters, there's a distribution from which it picks the data point, like a Gaussian distribution, let's say, and then it throws at me that point. So that's the assumption I'm making about the nature process by which it generated for me these clusters. Of course, the real nature process can be much more difficult than what I just described. But what we're doing now is we're assuming that that's the nature process, and we're going to try to get as close to the nature process as possible under the assumptions we just made. So what we want to do is, again, think about this clustering from that probabilistic modeling perspective. And the way to do that is we need to think about a latent structure like the one we just described. So what I just said is summarized here. So we're saying that nature's hidden process is something like this. So we have a finite number of clusters, so say 3. And then each cluster has some distribution. So these are the Gaussians you see here. And then what the nature does, it samples a cluster. So it says, I'm going to pick cluster number 2. From cluster number 2, then it samples from this Gaussian a data point, and it decides to show it to us. So the idea here is, again, that this process is what nature is doing, and we're going to try to model that process. Again, this is not the real process. This is our assumption of the process, that we can get as close as possible under our assumptions to the real hidden process done by nature. So now, because we have 2 types of variables, so we have the number of clusters, which is discrete, so that's kind of what nature picks first. And we also have a continuous variable, which is like the location of the point. We have 2 types of random variables to understand. We will need a continuous random variable that will give me the location of these green points. And we will need a discrete random variable that is like the finite k number of clusters. So the idea is that nature is picking from some distribution which is categorical, the cluster class, and from that cluster class, it is picking the relevant data point according to this like Gaussian distribution to show it to me. So now we have to be able to deal with these two. So we have a continuous random variable conveying the exact position of the point, and we have a discrete random variable which is conveying the choice of the cluster. So because they're random variables and we want to deal with distributions, we're going to assume some distributions over them. So for example, Gaussian distribution is just this bell curve, which we're going to assume on a continuous random variable. And a categorical distribution or a multinomial distribution is the distribution we're going to assume on the number of clusters. So C equals 1 means that it comes from the first cluster, 2, second, 3, third cluster. And now the size of the bar graph here is just conveying how much the probability is that I pick cluster 1, cluster 2, or cluster 3. Right. So now in order to model this process as we agreed, we're going to have two types of random variables, a continuous one and a discrete one. So what are we going to do with these? So what we're going to say is that we're going to say that the cluster centers are sampled from the Gaussian distribution. So remember, these are the centers here, right? And we're going to say that these centers are sampled from this Gaussian distribution, where we say we know the mean and the variance of that Gaussian distribution. And as you remember, we have big K of them, right? So we have big K different clusters, 3 clusters. Each cluster has a Gaussian distribution, and that Gaussian distribution has a mean that is sampled according to some 0 and sigma squared. So now it's interesting that what I'm conveying to you here is my prior beliefs on these, right? So that's why this is the systematic way of dealing with my prior beliefs, because I'm saying, okay, look, there's a set of Gaussians from which the cluster center is picked. And that cluster center, given the cluster center and the accompanying cluster, then I can generate a data point. So let's see how we do that. So we pick now the cluster center. The next thing we need to do is we need to pick a cluster choice, Ci, from some categorical distribution of K. So the idea here is that we assume that a cluster is a one-hot vector. So that's like, for example, in this case, it's going to be 1, 0, 0 for this cluster, 0, 1, 0 for this cluster, and 1, 0, 0 for this cluster. And then we're going to have that picked from some discrete distribution over that one hot representation, and that is categorical of K. At the beginning, we're going to assume that these are kind of uniformly sampled or equally likely sampled, and we do that for every data point I. So we pick first of all the cluster center, then we also pick the cluster itself. Now, how do we observe the data? Well, the way we're going to observe this data point xi, we're going to condition that on the cluster center it belongs to, and on the mean vector collecting all these means here. So now what is this Ci transpose mu? Well, it is simply the following. Ci is just a one hot vector. So Ci sampled from this is just a one hot vector. So it's a vector of Ci equals 0, 0, and it has 1 in some component, and everything else is 0. And of course it has size K. Mu is the vector of all these centers that we have sampled here. So that's kind of the vector of all the means. So now once I do this inner product Ci transposed X, then I just multiply this one hot vector by this mean vector. And since the 1 belongs on the third location in this one hot vector, then I just get mu3. So all this is saying is that if this happened to be the case, right, if it happened that the Ci transpose vector for point I had 1 in the third position, it's saying that the distribution of data point xi conditioned on this vector I've seen Ci and this mean vector mu is most likely going to be coming from the cluster center 3. So the idea here is that to observe the point xi, we had to pick some cluster center Ci and some mean vector mu. So that's why it's kind of a hierarchical structure, right? The idea is that you pick first the cluster center, you pick corresponding to that cluster center is a mean value, and from that mean value with some sigma 2 squared variance, which I don't know, we're gonna fit that, we end up knowing what the value of xi is. So now let's recap and understand what we've just done. So we thought about clustering from a probabilistic modeling perspective. We said in order to observe one data point, we're gonna have some Gaussian that has its center around some one hot vector, around the inner product between one hot vector and a vector of all means. So, and that's what you exactly see here. And now with this, if we are able to find the best distribution from which these means and these one hot vectors are sampled, then we effectively solve the clustering problem. So now let us recap what we had. So remember, we wanted to maximize log p of x, which we said is nothing but log of the marginal of p of x and z dz. And then we said using Bayes rule, that's p of x given z times p of z dz. And then we said how to compute this integral. So we went and gave this example here. So we said, okay, in the Bayesian mixture of Gaussians, which is kind of our clustering example we were describing above, we're going to sample some means from some Gaussian with the zero mean and sigma squared variance. We're going to sample some one hot vector from some categorical distribution. Again, our prior says it's going to be equally likely sampled. And now that gives me xi conditioned on ci to be written in this inner product form. So now with this, our goal is to maximize the marginal, right? So, okay, so we want to maximize log p of x. And now log p of x, as we said, we're going to integrate out the latent variables. And as you see, the only thing we observe in our example were the inputs. So we introduced two latent variables, being the cluster centers and the cluster means. And that's why, in order to get log p of x, we're going to marginalize out the joint distribution between the things we observe, the first latent variable c and the second latent variable mu. So we need to integrate out c and mu from the joint of x, c, and mu. That will give me p of x. Now integrating them out, notice that one of them is a discrete random variable, the other one is a continuous random variable. And that's why with respect to the continuous, I can just have the integral. But with respect to the other discrete random variable, I need to have the summation. So effectively, what I've done here is I just went from a marginal of the joint of x and latent variable 1 c, latent variable 2 mu, and then I integrated them out and I summed the c, sorry for that, and that gave me log p of x. And now my goal is to maximize log p of x, which means I want to maximize this. Right, so now let's understand this. So right, so what about this crazy joint distribution? Because this joint distribution is not hard really, it's not easy because it has some discrete and some continuous random variables. So let's try to understand how we can factor this. Now, what we're gonna do is we're gonna try to factor this joint distribution of x, c, and mu. And to do that, we're gonna simply use the chain rule of probability. So the chain rule says that if you have n joint events, so you have an dot dot up to a1, the way you would factor that is you would take the last one conditioned on everything else. So you'd say it's p of an conditioned on an minus 1 up to a1, and then you multiply by the joint of the remainder, which is an minus 1 up to a1. So simply you condition the last one on everything else, then you multiply by the joint of everything else. It's really easy to show this. I mean, this is just like, again, Bayes rule. You can actually apply this and you would get here. But now the cool thing is that you can keep applying this over and over again. So now remember that we're going to take an minus 1 up to a1, and we can apply this chain rule again. So we can condition an minus 1 on an minus 2 up to a1, and then multiply by the joint of an minus 2 up to a1. So now let's apply this chain rule idea to our equation. So remember, we had n data points, n x's, so we have p of x1 up to xn. For every data point I, we also had a c vector, so that's c1 up to cn. And we had one fixed k component of a Gaussian means, which we wrote as mu1 up to mu k. So applying this chain rule equation here, we end up with the following. So we take xn, so that's like an, and we condition on everything else, which means we condition on xn minus 1, x up to x1, cn up to c1, mu1 up to mu k. But now notice that xi depends only on ci and mu I, and that's why you will end up with xn given cn and mu. And then you repeat that for xn minus 1, xn minus 2, up to x1, and then that gives you this product you see here. So that's why we have p of xn given cn and mu, and then you have p of x1 given c1 and mu. And then also don't forget that while you're doing this factorization, there will be a remaining joint, which is c1 up to cn and mu1 up to mu k, right? And now the idea is that once you condition cn on c1 up to cn minus 1 and mu1 up to mu k, you realize that in fact, because of our assumptions that we made above, then cn does not condition on anything, so it's just p of cn, and similarly does mu, so that's why it's just p of mu. So in fact, we can rewrite this joint as nothing but p of mu as times the product from I equals 1 to n of p of ci times p of xi given ci and mu. So again, remember, we were doing this because we wanted to maximize log p, which means log of this integral, and the summation of the joint. And now remember that we have the joint being factorized in this way. And how we factorize that is using the chain rule of probability. And it's really easy to factorize by just remembering our modeling assumptions, where x depends on c and mu, but c depends on nothing, as well as mu depends on nothing. Good. So now, once I plug this in here, then I get this equation, which is log of integral of p of mu times that product from I equals 1 to n. That's what you see here. And then don't forget that we had the summation over c, so the summation pops up here. And now you have p of ci, p of xi given ci and mu. Now, as you see, this is an extremely hard integral to compute. And because like these equations don't kind of like conjugate to each other, so it's really hard to deal with. And this is where variational inference pops up. So again, there are other sampling techniques which we're not going to go through because they're not as scalable as of today to solve these problems, and that's why we're going to go to variational inference instead. However, we have to put a word of caution. With sampling methods, there are actually theoretical guarantees that whatever you sample from will end up to be the posterior of what you're interested in. When it comes to variational inference, this is less likely so. So you don't have really much theoretical guarantees on what's happening when we do such approximations. But experimentally, these things seem to be working really, really well. So how does variational inference deal with this integral? And that's what we're going to talk about in a second. So let's go back to the general form. Remember that we had our marginal, and we said that the marginal is nothing but log of integrating out this joint of x and z dz. So the way variational inference works is that it introduces some other distribution, which we call the variational distribution, and that's what we call q of z. So now you have integral of q of z over q of z. Now, as you see, this is 1, so I didn't affect the equation. That's why it's an equality. And then this is nothing but log of e over q of z of p of x and z over q of z. Remember that the integral of q of some distribution q multiplied by some function dz is nothing but the integral of that function, right? Nothing but the expectation of that function, right? So the idea here is that you will have the integral of q of z times this ratio, which is nothing but the expectation under q of z of this ratio, which is p of x and z over q of z. So again, what we've done is we introduced a variational distribution over the latent variables, and then we just wrote that as the expectation. Now what we're going to do is we're going to make use of Jensen's inequality, which says that log of e of q of p x and z over q of z is greater than or equal to e of q of z of the log of p of x and z over q of z. So effectively what I've done, I was able to take the log inside and have a greater than sign by just simply applying Jensen's inequality. If you don't know Jensen's inequality, that's okay. Just have a look at it. It's really just providing a nice bound on some phi of expectations, where phi are either convex or concave functions. So this is like a nice inequality which we use here. And since we're maximizing this, greater than is fine. Now what we're going to do is we're going to just now start factorizing this a little bit. Remember, this is a joint, so I can use Bayes rule. And Bayes rule would tell me, okay, I'm going to have E over Q of Z log of, instead of the joint, I just write X given Z times P of Z. That's just simple Bayes rule. A and B is A given B times P of B. And now I use some property of the logarithm where it says that log of the product is nothing but the sum of the logs. So now you'll have log of P of X given Z plus the ratio of P over Q. So you end up with E log P of X given Z plus log of the P of Z over Q of Z. Now we can take the expectation, because the expectation can be commuted across the sum. So you can say this is E of that plus E of that, which is nothing but E of log of P of X given Z plus E of Q of Z log P of Z over Q of Z. Now, we realize that because there's a log here, I can flip these. So I can write this to be Q of Z over P of Z to the power minus 1. And log of something to the power minus 1 is nothing but minus 1 log of that something. And that's why you see the minus sign here. So you will have minus E of Q log of Q over P. And that is nothing but the definition of a Kullback-Leibler divergence, over KL divergence, which will give me this equation. So it will say that the log of the marginal is greater than or equal E of Q of log of P of X given Z, and that is kind of a regularizer. So now, although we did some math, this is a very intuitive equation really, because when you're trying to maximize this, what you're trying to do is you're trying to find some Q that maximizes the likelihood of you seeing your data from your latent, but also it's forcing you to not deviate a lot from your prior P of Z, because this is kind of like a regularizer. So it's saying, okay, whatever you do here, because there's a minus sign, try to minimize the distance to your prior. So it's kind of like I put my prior belief, I believe that's what's going to happen. And now this equation, in this equation, it popped up that, okay, let's try to fit the data we've seen, but also let's not deviate a lot from our regularizer. Now, please note that I came here to this equation, to the evidence lower bound, or the ELBO, from the marginal. Okay, you could have done this equally from the posterior. So you could have started, I want to try to minimize like the divergence between the approximate posterior and the real posterior, and then you could have worked through it. You would get to the exact same equation. Actually, that's left like an exercise for you to do. I mean, feel free to do that, write us, and then we will be very happy to look at it. Good. So because we're gonna also be interested in some further derivations, we just will show one other way to rewrite the ELBO. So remember that we started from here, so that's EQ of Z log P of X given Z minus the KL. So that's exactly what we reached to here, right? What we're going to do now is we're going to say, okay, let's introduce the Kullback-Leibler divergence, and that's just Q of Z log Q over P. And then we can, the log of the ratio can be split into the log, like log of A over B is log of A minus log of B. And that's why you get log of Q minus log of P. But because there's a minus sign here, this becomes a plus. And then you end up with EQ log P of X given Z minus the integral of Q of Z log Q plus Q of Z log P. Again, all I've done here is I just said log of A over B is log of A minus log of B. And then notice that log of P of X given Z and log of P of Z, they can be together, where we took Q of Z as a common factor. So how we did that, remember that the expectation is nothing but the integral of Q of Z log P of X given Z. And now we have another integral of Q of Z log of P of Z. And therefore now you can take Q of Z as a common, and then you would have that. And then this is minus integral of Q of Z log Q of Z. Then we can apply the Bayes rule again here in order to get the following. So in order to get this equation. However, before doing so, I just want to mention that please notice that log of P of X given Z times P of Z, where did that come from? It simply came from the fact that log of A plus log of P is log of A times B. and that's why it's p of x given z times p of z. And now using the bias rule, we can write that as the joint of q of z log p of x and z dz minus q of z log of q of z, and that is e over q of z of the joint plus some entropy term. So that minus that integral is nothing but the definition of the entropy. So this is another way we will write the ELBO, and the reason we did that is because now we're going to continue with our Bayesian mixture model that we were describing, and we will need this equation in order to derive the update rules. Great. So now, so since we've been here, right, so where we have written this, or equally we have written this, now what we need is we need to make an assumption about what type of variational distribution we are going to use in order to conduct our updates. So a very common way of doing that is to assume a mean field variational distribution. So that mean field variational distribution simply says that the joint over variational joint over q of z is nothing but the product from j equals 1 to m of q of j z of j. So each latent is covered by its own variational factor, and then there's a distribution over these latent variable which we will be trained by to maximize the ELBO, right? So now this is a big assumption, right? So this is that's why it's called mean field variational distribution assumption. And now that assumption is interesting. However, there are a lot of works today trying to get rid of that assumption because in a sense it can be restrictive. So there's a lot of work doing that. We will dive into these later. But now the idea is that you will use your ELBO, your evidence lower bound, and instead of this q of z, we will assume our mean field variational distribution, and we will use that to maximize the ELBO. So in our example, we had two latent variables, our vector of means and our c vector, the categorical one-hot vector. And now our variational distribution, we will introduce it on q of z, which is the latent variable, which is equivalently q of mu and c, right? Because these are our latent variables. Using this assumption that these two are independent, we write this as the product of q of mu times q of c. And now mu is a vector, so that's why it's q of 1 mu1 to mu k, q of c1 to cn. Now please, because again c is per one data point, and now remember our mean field variational distribution. And now what we're gonna do is we're gonna just write that as the product of the qk, let's say, or q of mu k phi k. So I can write it as qk, or I can just say it's parameterized by its own variational parameters phi k. And similarly for qc. So phi k and phi I, var mu and var c, these are variational parameters of the distribution that I'm gonna try to fit. All right, too much info. Let's recap. Remember, we started from the idea that we want to maximize our marginal. And we said in order to maximize the marginal, we assumed there's some latent structure. So we said, okay, what we're seeing as the marginal is just the marginalization of the latent structure or the latent variable. Then we said, using bias rule, I can write it like this. However, this is very hard to compute. And we gave the example on the Bayesian mixture model where we saw that this integral can become really, really, really messy, something like that. And that's really hard to compute. So then we said, okay, the cool thing about variational inference, or what is variational inference, is a way aiding us in computing this integral. And in fact, all it's going to do, it's going to transform this integral into an optimization problem. The way it does that is by introducing this variational distribution over the latent. And then we worked through it through the Jensen's inequality here. And then we reached this equation where we said, okay, now our goal is to maximize the likelihood while being close to my prior assumptions. So now notice that this integration, which was extremely hard to compute, now got transformed into an optimization problem for which we can, like, for example, have a Adam type solver, like, you know, like maybe you want to check the Adam videos before in order to see how Adam works and how it converges. Then we said, okay, we cannot do it under any generic q of z. We need to make some assumption about q of z. And then we introduced the mean field variational assumption that allowed us to write q of z as this product. Then we substituted it in our ELBO, and that would be our q of z. Then we went back and gave the example, our running example about the Bayesian mixture of Gaussians. And then we said, okay, Z is a vector of mu and C. And now we're going to make the variational, the mean field assumption here, where we're going to be able to write that Q as the product over the K dimensions of each of the mu's and the I dimensions of each of the C's. As we said, phi k var mu and phi I var c are unknown hyperparameters which we will train. So for example, we will say there's a Gaussian that has a mean parameterized by this phi that will generate for me this data. So I'm going to try to maximize my ELBO in order to find the best phi that regenerates my data. Great, so this is where we reached now. We understand what an ELBO is. We understand what a mean field variational distribution is. Now let's go back to our running example, use that in order to see how we can make an untractable problem transformed into an optimization problem to be able to integrate. Right, so now please recall that in one of the equations here, we will able to rewrite the ELBO as the integral of q and z log p of x and z dz and the entropy term. So now let's start from this equation in order to plug in our assumptions here and see what happens with the hard integral we had before. So remember, again, we had the integral of q of z log p of x and z minus the entropy term. And now we want to understand what happens to this problem. So let's start with the integral of q of z log p of x and z dz. Remember, q of z is our variational distribution, which will become later parameterized, and we want to find its parameters. So remember that z is nothing but the mu and the c, right? So as we said in this slide here, the latent variables in our Bayesian mixture of Gaussians is just the collection of the vector of means and the collection of one hot vector c's. So now, instead of z here, we're going to be substituting the q, mu, and c. And instead of z here, we're just putting mu and c. And now please notice that instead of just having one integral, we have an integral and summation. Again, mu is a continuous random variable, so we need an integral. C is a discrete random variable, so we need to have a summation. So now, effectively, what this has done is it marginalized out the latent variables q and z in order for me to get back to my marginal. Now, under my assumption, I said that I will split the q, mu, and c into q of mu times q of c, and that will allow me to just rewrite this into this form, q of mu times q of c. And now we derive before p of x and c and mu as this equation, if you recall, p of mu times the product of p of ci times p of xi given ci and mu. Sorry, there's a comma here that's missing. So what is this doing? It's simply, remember when we used the chain rule to factor our joint distribution? So I just took the resultant and plug it in here. So that has this form. So now remember that I can split the log, right? So I can say this is log of p of mu, then log of this product becomes summation of log of this, plus another summation of log of that. So now notice that log of p of mu only depends on mu, and that's why this becomes integral over q of mu log p of mu, which is nothing but the expectation of q of mu log p of mu. Similarly is the case for q of c. So q of c, where did this come from? So log of product of I of p of c is nothing but the summation of log of p of c. That's the summation of log p of c. And now you will have summation over c, q of c, log p of c, or summation over I of log p of ci, which is nothing but the expectation over q of c times the summation over I of log of p of ci. Lastly, for this term here, we have the same idea. Log of the product of p of xi given ci is nothing but the summation of log of p of xi given ci. And now we also have the integral and the summation of q of mu and q of c. And please notice that this will depend on both c and mu, and that's why we have expectation over both. So Our first term from the ELBO is nothing but E over Q of mu log P of mu. Remember, mu is nothing but this vector of means, which we assumed are coming from Gaussian. Ci is nothing but this categorical distribution, which we assume at the beginning is equally probable to be sampled. And remember that this dude right here is nothing but the Gaussian with the inner product mean and some variance. So now let us dig deeper. I mean, these are just equations, like digging deeper into the above. So let's start with log P of mu. Log P of mu is nothing but log of P of mu1 up to mu k, which is because we assume that mu1 up to mu k are sampled IID, then we can write that as the product from j equals 1 to k of P of mu j with the log. Remember that log of a product is summation of log, and remember that the P was a Gaussian with 0 mean and some sigma squared covariance. So what you see here is the equation of P of mu j, which is nothing but an equation of a Gaussian with a 0 mean and some sigma squared variance. So you will have log of 1 over square root of 2 pi sigma squared, exp of minus 1 over 2 sigma squared, and you typically have here mu j minus mean squared, but the mean is 0, so that's why it's mu j squared. Now, log of product is again the sum of logs. So now you have log of the first term and log of exp of minus 1 over 2 sigma squared mu j squared. But log of exp is nothing but whatever is in the exp, right? So therefore, it will be minus 1 over 2 sigma squared mu j squared. Now notice that this term here can be rewritten as minus k over 2 log of 2 pi sigma squared. The way you would do that is really simple. I mean, notice that you're summing this k times. And notice that log of 1 is 0, and you can write the ratio as log of 1 minus log of that, so you end up with this equation. And now you would end up with this term here, which is nothing but this term right there. So you end up minus summation j of 1 over 2 sigma squared mu j squared. All right, all good. So we understood this first chunk of this equation. And now we understood the second chunk of this. We need to understand this second chunk of this equation. And remember that P of Ci is a categorical distribution. And we assumed that our prior says every one hot vector is equally likely to be sampled. And that's why P of Ci here is nothing but 1 over k. And now the remaining term we would need to understand is what about log of P of xi given Ci and mu? Well, we can do the same thing. Remember that xi given Ci and mu is sampled from some Gaussian distribution with a mean of Ci transpose the mu. And that's why once you take the log, as we did here, but now with the correct mean, you end up with this equation. This corresponds to 1 over square root of 2 pi sigma squared, which is just the constant for this Gaussian. And now you have log of exp, and log of exp becomes whatever is in the exp, and you have this equation, where you have the random variable xi minus the mean, which we said is Ci transpose times mu. So now we can further expand this by like saying a minus b squared is a squared minus 2ab plus b squared, which will say this is xi squared minus 2Ci transpose mu xi plus b squared, which is Ci transpose mu squared. And now we write it component-wise. So we say, okay, this is xi squared minus 2 times the summation j from 1 to k of Cij mu j xi. So what I have done here is that I just expanded this to say that the vector C transpose is a row vector which has Ci1, Ci2, Ci3 up to Cik. Remember, Ci is a k-dimensional vector. And the mu is again a k-dimensional vector which has mu1, mu2 up to mu k. And that's why now Ci transpose the mu is nothing but Cij mu j xi, and there's a summation over its k components. And also notice that this squared is nothing but Ci transpose the mu, Ci transpose the mu, right? So that's just this squared. So now elaborating this, what you can actually do is you can rewrite this as the you can transpose any element of this, and you can write this as mu transposed Ci transposed the mu, which means that it is just a norm of mu squared multiplied by the corresponding components of Cij. And that's why you just get here the summation from j equals 1 to k of Cij mu j squared, where this is just the norm of the vector mu. And now notice that in fact this you can also introduce a summation over j for, because it really does not depend on j at all, and with its corresponding Cij value, and therefore you can rewrite this into this equation. In fact, how to go from here to here is a bit tricky, but it's not so difficult. So maybe it's interesting for you to have a look at that and trying to prove, how we can go from here to here. And if you tell us in the comments or send us an email on our emails on how you did that, we can have a look at that. But now what's interesting is that with this, we can rewrite this equation as minus 1 over 2 sigma squared summation j equals 1 to k of Cij xi minus mu j squared. Now remember, where this comes from is really nothing but this is xi squared, then you have minus 2 mu j xi, and you have mu j squared. So really what's missing from going from here to here is kind of a smart way to introduce Cij. So let's think, or you can think how you can do that, and just let us know. All right, great. So we worked through this and we arrived to this equation. So now this term in the ELBO, which was nothing but EQ log P of mu, then you had EQC summation and of log PCI, and then you had EQ of mu Q of C summation of XI given CI. Now we just plug in the results we got here, here, and here into this equation, which will give me this following form. So it will be E of Q of that constant, then you have this mu J squared, remember? And then we remember we had here the prior saying 1 over k for P of Ci. So that's kind of like doing it n times, because I have I equals 1 to n. And remember that the summation over C of Q of C is 1, so that goes away. And then we are left with that other term, which we just derived. So this last term is nothing but this equation being substituted back here, this equation substituted back here, and this equation substituted back there. Good. So now that we understood what the first term looks like, let's look on to the second term, which is kind of the entropy term. So now again, integral of Q of Z log of Q of Z is nothing but the integral of summation of Q of mu Q of C log of Q of mu Q of C. Where did this come from? Again, Z is our latent variable. It had mu and C, and we assumed that the joint of Q of mu and Q of C is the product Q of mu times Q of C. And then we introduce the summation and the integral, because there's one continuous and one discrete random variable. And now we again split the log here, which is log of Q of mu plus log of Q of C. And then in turn, we just split the integral and the summation to their corresponding variables. So you will see that this is integral of Q of mu log Q of mu. And then this one is summation of Q of C log Q of C. Right? So how did this happen? Again, it's really simple. Just do this multiplication. So you'll get Q of mu Q of C log Q of mu. And now notice that Q of C can, log of Q of mu can go out of this Q of C, because it's kind of like a constant with respect to it. And there's a summation over Q of C, which will make it 1. And that's why you end up with this equation. Similarly here, the integral of Q of mu will make it 1. And that's why you end up with this equation. And now this equation is simply saying that's the expectation of Q of mu log Q of mu plus the expectation of log Q of C. Great. Which in other terms can also be further written as the summation over j equals 1 to k of log of qj plus the summation from I equals 1 to n of log of q of I. Why this happened? Remember, we had a mean field variational approximation where we said that q of mu1 up to mu k is the product of q of mu1 times q of mu2 up to q of mu k. And then we said that q of c is again the product from q of 1 up to q of n. And also remember that we said that these are parameterized, q of mu's are parameterized, and now we want to maximize the ELBO such that we find this value of the unknown or free parameters. Great, so far our overall ELBO looks like this. This first term here, remember this is our ELBO, right? So this is our ELBO. The first term is this, and the second term is that. So what we just did here is we introduced the first term, which is this, and then the second term, that is that. Now, remember our mean field approximation where we said q of mu is a q of c times a q of mu. And then what we did here is we just introduced this q of mu in this equation. So we said that, okay, q of mu is that product and q of c is that product. And that's why now we can introduce this assumption into this equation, allowing us to, in fact, be able to rewrite that the q of mu of this equation here is going to be nothing but the summation of E over Qj mu j. So as you saw, all we've done is just assume this distribution for Q of mu. And that's why this minus 1 over 2 sigma squared goes out. Then the summation of E of Q of j, E of Q of j mu of j, and then we had the n log k, and we have here the n log k. Please notice these are the same, it's just a typo. So this is the total number of data points here and there. There's no problems here. Yeah, so as you saw, this is a constant. It goes out of this expectation. This becomes this because we assumed this expectation, and this is, there's just a small typo, but like n should be big N or vice versa. And now similarly here, so for some reason we went from small n to big N or something, but the idea is that n over 2 log 2 pi sigma squared remains here. So that's n over 2 log of 2 pi sigma squared. And now Q of mu, Q of C, we can actually again write it as this mean field approximation, and that would lead to here, right? So that would lead to E over Q of I of Cij and E over Q of j mu j of xi mu j squared. Again, why? Because remember, these are independent, and then they are factored in this way. So that's why every data point has its own variational distribution, Qi of Ci, and similarly for every mean center, Qj mu j. We do this in the last term here as well, and that gives me this equation. Again, the only thing I've done is just substituted this in here, which leads to this, and substitute this in there, which leads to that. Great. So now we have our ELBO, and that ELBO is described in terms of this variational distribution. And now what I'm going to do is I'm going to say that the variational distribution has its own free parameters, and then I'm going to try to find the best free parameters to maximize the ELBO. So to do that, we're just going to assume that Qj of mu j is a Gaussian that has unknown mean phi j1 and unknown variance phi j2. So that's kind of the variational distribution I'm trying to look for. And similarly, I'm going to say that Q of I over Ci is again a multinomial distribution which has some probability for some jth factor to occur. And that that probability is phi ij of var c. So I don't know these phi's, and I'm going to try to find these phi's such that I maximize my ELBO. So just a word on notation, please notice that Ci is a one-hot vector. So now, in order to define that distribution over that one-hot vector, we're going to ask what is the density of having a Ci to be equal to a jth one-hot vector as given here, and that is phi ij in our example. So now what we're going to do is we're going to use these variational assumptions, plug them back into this equation, and then as just do gradients, set them equal to 0 in order to get our updates. Right, so we do that. Now we realize that, okay, let's start with this term, EQ of j mu of j squared. Well, okay, that can be easily observed to be written as phi of j2, which is like the variance plus the mean squared of the variational distribution. Okay, where did this come from? Again, it's an exercise for you to do, but it's easy to see. The place where this will come from is from the variance. Remember that the variance is nothing but the squared of the value minus the mean squared, right? And now if you have that equation and you work through it, you will realize that you can write E of Q of j mu j squared as the phi j2, which is the variance term from our variation distribution, plus the mean squared. Similarly, we can do for this term here, E of Qi Cij, E of Qj mu mu j, where we know that the Q of Ci, that the probability of Ci to occur is nothing but phi ij of that var of C, so you can write it like this. And E of Qj, again, we just use our assumptions we had here, and then you are able to write it in this form. So the idea is that, I mean, this might look tedious, but it's really easy if you just work it through step by step. The idea is that all we're trying to do is we're just plugging in our assumptions into this equation. Similarly, we can do for the entropy term, and that's kind of the entropy of the Gaussian. And similarly, we can do for the last term, which is just from this equation here. So to get this term, we just use the Bishop's definition of a multinomial distribution, which is nothing but the mean to the power of the value of the data point, and there's a product over that. And that's why if you have a log, then it becomes a summation of phi ij log of phi ij. Again, these steps are really simple. All you need to do is just plug in these equations here, and then you would get the following equations. If they are unclear, please let us know. We would be happy to help in deriving them together. All right, great. So now we have our ELBO, and now what is super cool is that our ELBO is in fact described in terms of the unknown free parameters, right? So we don't know the parameter phi j1, phi j2, phi ij var c. We don't know any of these parameters, but now we have an optimization problem which we can maximize with respect to these free parameters. So there are different ways to do that from here. Sorry. So there are different ways to do that from here. One way to do it is just to use Adam, for example. Another way to do it is we're going to try to get a closed form solution, which we can do in this simple example. And the way we do that is, right, so this is just plugging everything back in from the equations we had above. And then we have this equation. The way we're going to do it is we're just going to take the gradient with respect to each of the unknown free parameters and set it equal to 0. Okay, so let's do that with respect to phi ij var c. If we look at this equation, we realize that phi ij var c appears here, and that's why the gradient with respect to phi ij var c is 1, and that's why you get this equation here, which is nothing but that, really, right? And then right. So then what happens is that we just derive this with respect to phi ij var c. And there is something weird in this, and I think what is weird is that this should have been phi ij var c. So the reason is that so this is a typo. So the idea is that this phi ij var c is here, and phi ij var c is here. And now what happens is that this will be phi ij var c, and that's why once you do the gradient with respect to phi ij var c, this will still be there, right? So that's why you will have this term, and then you will have this term as well. So as you see here, where do we get this -1 minus log? Again, this phi ij var c, it should be a c here. And that's why now you have kind of x log of something, a derivative or gradient, and that's why you get this equation. So now solving this equation with respect to var c again, we will end up with this equation right here, and that says that this phi ij var c is proportional to this equation x of that, and therefore now given the values of the phi j1 var mu, phi j2 var sigma, and phi j1 var mu, which is just the mean of the variational and the sigma of the variational distribution, we can in fact update var ij. Now notice we need to make that a valid distribution, and that's why we need to normalize this, but it's easy to normalize it by just summing it across all j's. We can do the same for var j mu, and that again we just derive this with respect to var j mu, and then that would give me a closed form solution for phi j1, which is the mean of the variational distribution. And then we can do the same with respect to var j sigma, which again will give me this equation for the variance of the Gaussian distribution. So now this is pretty interesting, because now we have all the values of the unknown parameters. And then what we can do is we can in fact, given these parameters, just maximize this equation with respect to these unknown variational parameters. Will give me this equation. And then I can use that in an algorithm in order to fit my Bayesian Gaussian mixture model. So we didn't code this up, but then we found some very interesting code from Zia Zhu. This code is available online. This code is kind of doing something very similar to what we described. The difference is up to some constants between what we have and what he has. But so please have a look at this code, which we think is really interesting. So the blog that was written has some typos in it, but hey, as you see, we also have some typos, so it's okay. But then this is a very nice piece of code which actually seems to work for a Gaussian mixture model. And what you see here is you have an ELBO definition, which S is what we called our variance, and M is the mean. And then the idea here is that we have an update phi function and an update mu function. And then the idea is that if you see here, the update phi function will have the self.phi, which is nothing but exponential of this exponent, which has the mean squared and the variance, right? And now if I look at my equation here, I have kind of like the mean squared, as you see there, right? And then you have the variance. And then what will happen is we will just normalize that, as we said, because that's a distribution, and that will do the update of the phi. Again, please notice there's a minor difference in constants between us and this code, but it's still along the same lines. And similarly, you can do the update for the mean. So again, the update of the mean is from the equations we got above, so you can update the mean and the variance, and then you have an update for the mean and you have an update for the variance, and then with that you can fit the ELBO. So what the fitting does is simply it's a loop, and then the first thing it does is it calls CAVI, or coordinate ascent variational inference. This CAVI updates the mean and the phi's. After it updates the means and the phi's, it just repeats for some maximum number of iterations. And this whole process repeats and repeats and repeats until a tolerance is achieved, so less than a tolerance, which is set in this case to e to the power minus 10. This equation here is the ELBO, and that's what we just derived together, really. And that ELBO is what is going to be used in order to take the gradients for our updates. Right. So now we just downloaded this code and we ran it, and then it's interesting to see that, okay, so this is the code. And on this upper side here is kind of the real data. So that's kind of what the data points are coming from. They are coming from these distributions. And after running this code, what you will get are these black lines here. And these black lines are the fit of this CAVI, or coordinate ascent variational inference, to this data. And as you see, it's kind of a good fit, right? Like, I mean, it fits really well. The problem, however, is that when we go to higher like mixture components, I think I had here like 5 or 6, and then you can start seeing that this does not really scale well. I'm not sure if this is a problem with the code, which I don't think so. It's maybe because of CAVI itself is not so scalable algorithm. And that's why in the next lecture, we will be describing the reparameterization trick and stochastic gradient variational inference, which would scale much better. Right, so there was a lot of math in this lecture, but I hope that we have given you some a concise introduction to variational inference. So we described the ELBO, we described how you can optimize for the ELBO, we described what a mean field approximation means in variational inference, and our material is not self-generated. It's taken from this very awesome survey from David Bly and colleagues called Variational Inference, a Review for Statisticians. I believe this is one of the best papers out there as a survey on variational inference and a review. It's really great paper. I advise that you have a look at it and read it thoroughly. What we try to do here is that there are some steps that are skipped in this variational inference review, and what we try to do is we try to clarify each of these steps. We hope we made that intuitive enough. If you have any questions, please ask them in the comments below. We will be very happy to do that. And then here, I just put some codes available. So this is something we ran, we just described. But there's also Sky, how do you pronounce this? SCI-Kit. Sky-Kit Learn does also Gaussian mixture models. It's actually, I used this before. So in sklearn, it actually works very well. And there's one also in PyTorch, which I found on this link, which might be also very useful to have a look at. Right, so now you know what variational inference is. You know why probabilistic modeling is important. We did here a derivation on a example of a Bayesian Gaussian mixture model. And we derived the ELBO, we put in the equations, and then we derived the update rules. and then we showed a code of how this thing would work. In the next lecture, what we will be digging into is a different way to solve this ELBO. So rather than just doing this closed form solution, so to say, that we got, what we're going to be doing is more like the reparameterization trick, more like a scalable solution. So that comes next. So I hope you liked this video, and please make sure to share, like, and subscribe, and see you in the next lecture where we will be describing more about variational inference. Thanks.